Today, we are going to discuss the Schrodinger equation. The Schrodinger equation. Okay, the Schrodinger equation. The Schrodinger equation. That is what we're going to discuss today. The Schrodinger equation. This is a very pronounced equation, a very important equation that discusses the hydrogen atom, or specifically we could say it discusses the electron in around the nucleus of an atom. And the hydrogen atom was taken as the basis for the discussion of the Schrodinger equation. I want to let us know that the work on the electron around the nucleus of an atom had already been discussed by Niels Bohr, but there were some deficiencies in the course of his discussion that gave rise to Schrodinger, who later was able to bring out an equation that explained the nature of electron on around the nucleus, and how you can also solve it. Let us write down this particular equation and see how it looks like. This Schrodinger equation is written as minus a square all over 8 pi square m bracket partial differential square of this over s square plus this all over the y square plus this all over the z square plus v this equals to e this. This is the Schrodinger equation, a very prominent equation in chemistry to discuss the nature of electron around the nucleus of an atom. It's important for us to note what this whole thing represents. This sign you see written here is called the wave function, and of course the wave function has an equation, so the wave function can also be defined as a to the exponent of minus r over a over AO. Now, where of course this is the Bohr, this is the Bohr radius, and then this of course is the distance of the electron from the nucleus of an atom. So this is the wave function, and that is one of the very important parameters that Schrodinger was able to bring out in his navigation around the activities of the electron around the nucleus. And this is of course the E is the total energy, while the V is the potential energy, and the whole of this is the kinetic energy, while this is the potential energy and this is the total energy. Know that of course in your normal energy equation, total energy is equal to potential energy plus what? Kinetic energy. Now in this kinetic energy you have h, which is the Planck constant. You have, this is the pi representation, and this is the mass of the electron. Now all these things you have inside there is just letting you to know that for you to be able to calculate the kinetic energy, you must differentiate twice the wave function with respect to x, y, z, which is the direction to which the electron moves around the nucleus of an atom. Now, having taken note of this, it's important for us to know that the relevance of this particular Schrodinger equation builds on 3 or 4 major things, and one is the presence of the wave function. I want us to know that before now, Niels Bohr believes that the electron that revolves around the nucleus of an atom is always found at a particular point. That was his statement. That was his own postulate, that you can find an electron at a particular point of an atom. That means he believes that if this is the nucleus of an atom, that there is a shell or a part where an electron can be found. And he believes that this electron that can be found must be found at this particular point of what of the parts. Now, but because of Schrodinger, he took upon himself to understand more about the nucleus of an atom and also the electron the possibility in terms of where you can find it. He believes that with the help of the wave function, then there is no way one will have been thinking that you can find an electron at a particular point. And this his theory negates that of Niels Bohr and became a prominent theory in chemistry to explain the hydrogen atom, especially the relationship of the electron with the nucleus. So now, according to Schrodinger, with the help of what the wave function, which is represented by this, you can only probably visualize an electron at a particular region of the space around the nucleus. He said, according to him, that there are infinite points, according to Schrodinger, there are infinite points around this particular nucleus where electron can be found. So you can find an electron here, you can find an electron here, you can find an electron here, or find the electron here. You must not find the electron at a particular point because it's infinitely impossible. Since there are so many points, infinite points around the nucleus, then you can be able to find electron anywhere around the nucleus. But for you to be able to say that an electron is found at a particular area, then you should look at the probability of the concentration of that particular electron around the area. That means that while the electron can be found anywhere around here, there must be a particular area where that electron spends much time than the other places. Now, that place that it spends much time than the other places can be probably, that is the statement he used, can be probably said to be where you can find an electron. It does not mean that the electron is found only at that point. And that was a very big breakthrough for the area, or in the area of chemistry, for Schrodinger. So you can see that one of the relevance of the Schrodinger equation was to be able to understand where you can possibly find an electron and how you can calculate that. Now, another very important breakthrough in chemistry that Schrodinger equation introduced was the presence of other quantum numbers. Remember, Niels Bohr had already introduced the principal quantum number, in his work. But Schrodinger equation let us understand the fact that there is more than just the principal quantum number in the description of the orbitals. Now, from the work of Schrodinger, he said, yes, there is a principal quantum number. Principal quantum number, which he tagged n. And according to him, the principal quantum number seem to explain or govern the energy of the orbital. So he believes that you can be able to calculate the various orbital energies. And he introduced an equation here that represents that. According to him, En is equals to minus E for Me all over 8 square of this, S square, N square. He believes that this equation is an equation you can use to calculate the energy of of an orbital where electron is possibly going to be found. So with this you can calculate the energy, you can calculate the orbital energy for the 1s or the 2s or the 2p, or just like that. Now, this also was a breakthrough, and as far as Schrodinger equation is concerned, it is believed that you can determine the degeneracy of the orbitals. Degeneracy means the different energies the orbitals carry. Some orbitals carry the same energy, some do not. So with this, his introduction of the equation, it was it was possible for chemists to calculate the various energy at different energy levels, and then to understand which of the energy levels have the same or have different energies. And that contributes seriously to finding the electrons at different spaces, okay, different regions. Now, apart from this, he also was able to bring a breakthrough into another quantum number which we call the azimuthal quantum number. An azimuthal quantum number, he called it L. The azimuthal quantum number can also be called the subsidiary quantum number. And according to him, this quantum number stands to explain or govern what? Govern the shape of molecules, the shape of the various orbitals. You see, so he went further away than Niels Bohr to bring out things that you can be able to use to explain the nature of electrons around the nucleus. So according to him, he said not all the orbitals have the same shape. So you know that we have the s, the p, the d orbital, as the case may be. But let us know something very interesting. Why the name the s, the p, d, f, g orbitals, as the case may be. You know, Schrodinger decided to name his orbital based on two things: the principal quantum number and the azimuthal quantum number. So the principal quantum number comes with a number 1, 2, 3, 4, as the case may be, depicting the various energy levels or the various orbitals, while it also comes with a letter representing the azimuthal quantum number. Now, why the SPD he started was because of the earlier assertions from spectroscopy, where spectral lines were being seen from light. You know, talking about the wave particle duality. So where the spectral lines were seen from light. So the major spectral lines that were seen were the sharp lines, the principal line, and that is the sharp lines, the principal lines, and the D, which of course is the diffused lines. So he decided to use this particular spectral lines, of course, that was discovered in spectroscopy, to name his quantum numbers. That's why now we have the S, P, D, F, G, as the case may be. But back to the azimuthal quantum number, he said it governs or explains the shape of molecules, and that contributes seriously to understanding the space or region around the space where electrons can possibly be found. And according to him, we have the s orbital, and the s orbital he drew it in this form. So the s orbital, he drew it in this form. So with the s orbital, according to him, with the s orbital, you have the x, you have the y, and the z. And this is the s orbital. And the x, y, z are simply the points at which, or the directions at which, the electron does what? Moves around the nucleus of an atom. And he also said that the p orbital can be represented as this. So you can have the p orbital represented as x, y, z. And this is the px orbital. Of course, you also have the py orbital, as the case may be. So you can also have something of this nature that depicts x, y, z. So this is the py orbital, and you also have the pz orbital. And the orientation of these orbitals explain also the possibility of finding electrons in the region around the space of what? The nucleus. He also named the d orbital from the azimuthal quantum number that he discovered from his Schrodinger equation processes. He named the diagram of the azimuthal, of the d orbital to be in this format. Okay, so we have this, and we have this, and this is the x, and this is the y, and this is the z, and this is the d orbital. So the azimuthal quantum number governs or explains the orientation or the shape of what the various orbitals, and that was a very big discovery too for Schrodinger as far as his work in chemistry was concerned. And then we have another quantum number that he also was able to discover in the process of trying to understand what the nature of electrons around the nucleus, and that was the magnetic quantum number. He called it n. So from the magnetic quantum number, it was meant to explain the nature or the reaction of the electron around the magnetic field or around the electric field. And he believes that with the magnetic quantum number, his discovery was that there were two spins around the electron and the nucleus of an atom. He believes that there is a positive spin, which is plus half, and there is a negative spin, which is minus half. So he believed that from for example, like the 1s orbital is just one electron. So it means that if you have this, by right, you were supposed to have, if this is 1s, 1 for hydrogen, you were supposed to have only one spin, positive half. So it means that there is a deficiency already of the order. So with the magnetic quantum number, it was possible for chemists or scientists to be able to place the various spins according to their various energy levels, according to their various orbitals, and that is where you have the Pauli's exclusion principle came in. So you can see that so much was discovered by Schrodinger as far as the work on understanding the nature of what the electron around the nucleus of an atom. And hydrogen atom was used principally because it's quite simple and easy to manipulate. If you want to calculate using other elements, you will see that it's quite cumbersome, but the work can still be done. So I'm sure that today's class, you have learned something so seriously about the Schrodinger equation, the almighty Schrodinger equation. Until our next class, please do not forget to share, do not forget to like, do not also forget to subscribe and to comment. It is bye.